So now we're going to be looking at the law of gravitation. This is actually pretty straightforward equations. Most people don't find this like too tough, but we'll just kind of wrap up this section with the general equation we're always going to use for force of gravity is G times m1 m2 over r squared, where r is the distance between them, G is a constant, and these are the masses of the two objects. Now previously we always said force of gravity was equal to mg. But this is sort of an approximation near the Earth's surface. Okay, so we only use that when we're close to the Earth's surface. Otherwise, this is the more general. Even this is an approximation too, actually. The exact formula for gravity is Einstein's theory of relativity, which has curvature. It's way more advanced math than you would need. So even this one is actually a bit of an approximation. It's not exactly right either, but it's more accurate than this one. So calculate the Earth's mass given the acceleration due to gravity of the North Pole. Acceleration is 9.83 meters per second squared, and the radius of the Earth is 6371 kilometers. It's not centripetal, this is just acceleration. Okay. Compared to this accepted value. Okay, so we're going to look at this. The force of gravity at the North Pole is equal to m times g. But he's saying g at the North Pole is 9.83. The reason it's a little smaller, actually a little bit bigger, is because when you're at like the equator and you're spinning around, the Earth's actually kind of throwing you out a little bit. And so if you do the net force calculation, you find that gravity is a little bit weaker due to the spinning Earth, like the centripetal motion. Anyway, so that's equal to ma, or equal to ma. We'll call this a. Okay, and that's equal to g, mass of the person, mass of the Earth, divided by the radius of the Earth squared, if you're near the surface of the Earth. So this m's going to cancel, so acceleration is equal to this. And I can calculate for the mass of the Earth by solving for me, and I get a times re squared over g. Now a is 9.83. The radius of the Earth is 6371. But I got to put it in meters, so it's times 10 to the 3 meters squared, divided by universal gravitational constant, which is 6.67 times 10 to the minus 11. And that would be 9.83 times 6371 E3 squared divided by 6.67 E minus 11. And that's 5.98 times 98 times 10 to the 24 kilograms. That is pretty close. Pretty close. I don't know what they want in comparison. It's close. It's fine. What is acceleration due to gravity on the surface of the moon? Okay. Let's do it as a calculation. G m mass of the moon divided by radius of the moon squared is equal to m times the acceleration, or m times the acceleration due to gravity. So the masses cancel. So the acceleration due to gravity there is just g. So that's 6.67 times 10 to the minus 11. We need to know sort of mass of the moon. Let's get the mass of the moon. It's about 7.3435 times 10 to the 22 divided by the radius of the moon is what is its? I have it in miles, but I don't want it in miles. I want it to radius, polar radius. 1736 times 10 to the 3 meters. Okay. It should come out to be about 1/6 of Earth's gravity. That's the number I remember. Squared. All of this was supposed to be squared. 1.63 meters per second squared. If I multiply that by 6, yeah, it's about 9.8. Close enough. B, on the surface of Mars, do the exact same calculation. G times mass of Mars over the radius of Mars squared. Unfortunately, M is the same moon for Mars, so it's 6.67 times 10 to the minus 11 times mass 6.418 times 10 to the 23 divided by 3.38 times 10 to the 6 squared. .75 meters per second squared. So more than the moon, less than the Earth still. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.